Can you make it across the finish line when every step depends on your last? Jump Game is a Pattern Mastery 100 favorite and a classic at Google, Facebook, and Amazon, testing your greedy algorithms and array reasoning. 30% of candidates trip over edge cases or inefficient DP. Master this, and you'll breeze through reachability and greedy interview problems. Let's solve Jump Game using the basic approach, your step-by-step strategy for any reachability or greedy challenge. Given an array of non-negative integers, where each element represents your maximum jump length from that position, determine if you can reach the last index. List of integers nums, max jump at each index. Boolean. True if you can reach the end, else false. Picture crossing stepping stones in a river, where each stone tells you how far you can jump ahead. Interviewers might ask, how would you check if a player can always reach the end in a game with varying step sizes? What's tricky? DP is possible but unnecessary. Greedy works better. Watch out for zeros in the array, they can block progress if you can't jump past them. Must always keep track of the farthest reachable index. Initialize a variable farthest to 0. Iterate through the array. If the current index is greater than farthest, you're stuck, return false. At each index, update farthest equals max farthest, I plus nums I. If farthest ever reaches or exceeds the last index, return true. Initialize farthest equals 0. Loop over nums with index I. If I greater than farthest, return false. Update farthest equals max farthest, I plus nums I. If farthest greater than equals len nums, 1, return true. If loop ends, return false. Approach, greedy, furthest reach time complexity, ON. This line defines the solution class. In Java, all methods live inside a class, so this simply acts as the container for our logic. This is our main method. It takes an array where each number tells us how far we can jump forward from that position, and it returns true or false depending on whether we can reach the last index. Here we set up two variables. Reach keeps track of the furthest index we can reach so far, and n stores the length of the array. Think of reach as our current maximum power to move forward. This loop walks through the array from left to right. At each position, we check whether we're even able to land on this index. This is a critical check. If our current index I is beyond what we can reach, that means we're stuck. We can't even get here. In that case, we immediately return false. Pause. This is the fail-fast condition. Here we update how far we can reach. From index I, we can jump up to I plus nums I. We compare that with our current reach and keep the larger value. This greedy step always keeps the best possible reach so far. If our furthest reach already gets us to the last index or beyond, we're done. We can successfully reach the end, so we return true right away. This closes the loop. If we finish iterating without failing, it means every position was reachable. If we exit the loop normally, we return true, confirming that the last index is reachable. This closes the method. And this closes the class. Final wrap-up. And that's how this algorithm works. It first tracks how far we can reach, then greedily extends that reach at every step while immediately stopping if we ever get stuck. Efficient, simple, and elegant. Test case check, Jump Game using greedy reachability. Let's test our function using this input. 2, 3, 1, 1, 4. These numbers represent how far you can jump from each position, and our goal is to determine whether we can reach the last index. Here's why the solution works. We track the farthest position we can reach as we move through the array. If at any point our current index goes beyond this reachable range, we know we're stuck. Otherwise, we keep expanding the reach by taking the maximum of the current reachable distance, and the new jump range from the current index, I plus nums I. And that's exactly what our program outputs, true. The result matches the expected value, confirming that the greedy reachability method is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully checks whether we can reach the final index by tracking the maximum reachable position, efficient, accurate, and reliable. Approach, BFS traversal. Time complexity, ON squared, worst case. This line declares the solution class. It's the container that holds the method we're about to walk through. Here we define the method canJump. It takes an array of numbers and returns true if we can reach the last index, or false if we can't. This stores the length of the array in n. That makes it easy to refer to the last index as n1. This creates a queue for BFS. A queue works like a line. We add positions to the back, and we process them from the front, one at a time. This creates a vis array to track which indices we've already visited. This prevents us from reprocessing the same position over and over. This adds index 0 to the queue, meaning we start the search from the beginning of the array. This marks index 0 as visited, since we're already starting there. This begins the BFS loop. As long as there are positions in the queue that we still need to explore, we keep going. This removes the front index from the queue and stores it in I. This is the current position we're exploring. If the current position is the last index, we've successfully reached the goal, so we return true right away. Now we try every possible jump length from this index. If nums I is 3, for example, we try jumping 1 step, 2 steps, and 3 steps. In the worst case, trying many jumps from many indices can lead to O(n squared) time. This calculates the next index we would land on if we jump j steps from I. This checks two things. First, that nxt stays inside the array, and second, that we haven't already visited it. If the next index is valid and new, we mark it visited immediately to avoid duplicates later. Then we add this next index into the queue, so BFS will explore it in the future. This closes the inner if block. This closes the loop over possible jump lengths. This closes the BFS while loop. If we exit the loop, it means there are no more reachable positions to explore. If we never reach the last index, then it's not possible to jump to the end, so we return false. This closes the method. This closes the class. Final wrap-up. And that's how this algorithm works. It first initializes a queue and visited tracker starting from index 0, then explores every reachable index level by level using BFS until it either reaches the last index or runs out of places to go. Efficient, simple, and elegant. Test case check, jump game using BFS search. Let's test our function using this input. 3, 2, 1, 0, 4. These numbers represent how far you can jump from each index, and our goal is to see whether we can reach the last position in the array. Here's why the solution works. We treat each index like a node and perform a BFS search. Starting from index 0, we explore every reachable next position using all valid jump distances. We also track a visited set so we never recheck the same index. And that's exactly what our program outputs, false. This matches the expected value, confirming that our BFS exploration correctly detects when the last index cannot be reached. Wrap up. So, our implementation is correct. The algorithm successfully checks all reachable paths using BFS and accurately identifies when the end cannot be reached. Efficient, accurate, and reliable. Jump game. Let's do a recap. So, we've just tackled one of the most popular reachability problems in interviews, jump game. It's fast-paced, logical, and a great way to show that you understand how to balance dynamic programming ideas with greedy reasoning. Once you grasp this, you'll spot the same pattern in dozens of real-world and interview problems. Breakdown recap. At its core, the problem asks, can you reach the end of an array if each element tells you how far you can jump? It's like stepping across stones. Every number tells you how many stones ahead you can move, and your goal is to make it to the last one without getting stuck. Assess recap. We compared two approaches, dynamic programming and greedy. While DP works, it's unnecessary here. Greedy logic is more efficient. The key insight was simple. Keep track of the farthest point you can reach. If at any point your current index goes beyond that limit, you're stuck. Otherwise, you keep pushing that boundary forward. Structure recap. We structured it around one core loop, moving through the array while tracking the farthest reachable index. If the current position is ever out of reach, we stop. If we extend the farthest reach to or beyond the final index, we've made it. It's clean, linear, and effective. Implement recap. We ran the greedy logic step by step on LeetCode. The code executed perfectly, no runtime errors, no boundary issues, confirming that the logic holds even with tricky cases like zeros and single-element arrays. Check recap. All test cases passed. The algorithm successfully determined when the end was reachable, and when it wasn't. It handled small, large, and edge cases exactly as expected, efficient, reliable, and consistent. Closing insight. The key takeaway? Jump game teaches you how to think ahead, literally. It's not about every step, but how far you can go from each one. Mastering this greedy mindset will help you tackle a whole class of problems built around reachability, optimization, and forward-thinking logic.